is being
Okay, guys, so in this section, we're going to learn how to graph polar graphs by hand, but for the most part, everything we do with polar graphs in terms of graphing, we're going to do on the calculator, okay? Just because you'll see by this first example, it's kind of a big pain in the butt to graph these by hand. It's really hard. If you have special graph paper with a bunch of radii drawn on it, maybe that can help with a bunch of circles with different radii. But even then, it's still kind of tough. So what we're going to do is we're going to try to graph r equals cosine of 2 theta and see what we kind of get. So I'm going to pick some values, ones that I know off the top of my head, right? So I'm picking numbers that I know how to work with really good, or I should say angles. So I'm going to pick 0 for theta, and the cosine of 0 is 1, right? I'm going to pick pi 6 for theta, and pi 6 times 2 becomes pi thirds, and the cosine of pi thirds is 1/2. I'm going to pick pi fourths, and that would be pi halves once I multiply by 2. So I'm going to get 0. Then I'm going to get negative 1/2 for this one. I'm going to get negative 1 for this one, and I'm going to get negative 1/2 for this one. Okay, so now I'm going to try to graph this. So I'm going to go over angle of 0 and a radius of 1. So that would be right there. Okay, now I'm going to go over an angle of pi 6. Now pi 6 and then have a radius of 1/2. So if I go pi 6, maybe that's right about there, maybe, okay? So that's about 1/2 radius and then about a pi 6. Then I'm gonna go over pi fourths with my, or I'm sorry, not over, but I'm gonna go at an angle of pi fourths, but I'm gonna go 0. So that'll be there, radius of 0. Then I'm gonna go pi thirds and I'm gonna go negative 1/2 for my radius. So remember, pi thirds would normally be, pi thirds 1/2 would normally be right about there, right? However, because it's negative 1/2, it's actually over here. So I have to erase that one. And then we go pi halves. So pi halves would normally be 1. So pi halves, oops, let me do this right. So pi thirds 1/2 would normally be there, but because it's negative, we flip. So pi halves negative 1. So pi halves would normally be right here, but because it's negative 1, I can flip it to down here, okay? Let me erase that real quick. I'll put it down here, okay? And then because it's 2 pi thirds, 2 pi thirds is negative 1/2 would be probably right about here. That would be 2 pi thirds 1/2, but because it's negative 1/2, we have to reflect it over here. So I think it's right about there. So now it's kind of hard to see what that graph would look like. So what I'm going to do is I'm going to take my calculator and I'm going to switch it to polar form. So we're going to go to mode, and then we have to go down. We keep it in radians and go to polar form or polar coordinates. Okay, so now we're in polar, and now we get out of here. And then when we do y equals, it has a new way to graph. It says r equals what? So we're going to say cosine of 2 theta. And let me go window. I'm going to try to do window of negative 2 pi to 2 pi. And then I'm going to do a step size of 0.1. Let's see if that helps. And then let's graph this. Okay, so let me go my window. Let me make my y values a little bit different. There we go. Okay, so we get a rose petal. So now that starts to make more sense, because now I can see that this is that, then that, then that. And let's look at this again. Okay, so that's not so bad. So then that means I should have something like this, and then I should have something like this. Oops. Right, and then something like, oh, I can't draw, you guys, so just bear with me. This is always my least favorite part of the course. Okay, so we have this, and we got our rose. Okay, so this is a type of polar graph, r equals cosine of 2 theta. But as you could see, it would have been very difficult to get the full picture of it. So we're going to pretty much for the rest of this 9.2, we're going to always use our calculators to give us polar graphs, okay? So what we're just going to do for the remainder of this section is kind of identify what certain graphs are going to look like. So when we get a graph of the form r equals a cosine theta or r equals a sine theta, we will get circles. So here we have 2 cosine theta. So I'm going to come over here and I'm going to clear this. I'm going to go y equals 2 cosine theta. Let's graph that. So it's a circle with a radius of 1. So here's 1, 2. So it's a circle with radius of 1. And it's adjacent or it's tangent to the y-axis. So 2 cosine theta gives me that. Now let's look at negative 2 sine theta. I bet you it's going to be something like this. Because if cosine was adjacent to the y-axis, I have a feeling sine, or not adjacent, tangent to the y-axis, I have a feeling sine is going to be tangent to the x-axis. Let's just look. So let's try this one now. So let's go y equals, let's clear this, and let's do negative 2 sine theta. Oops. Graph. And then sure enough, there it is. And we get the same graph. That's a pretty bad one. Okay, so that's our circle that is adjacent to the x-axis, and it has a radius of 1 or a diameter of 2. So as you can see, this number here in front is what tells you the diameter of the circle, okay? So that's one that we can identify. Now there's this little group that has this form, a plus or minus b sine theta and a plus or minus b cosine theta. And based on the relationship between a and b, it creates different shapes. So here, if the relationship between a and b is equal, you're going to get something called a cardioid. Okay, so let's see what this looks like on our calculator. In this case, a equals 1 and b equals 1. So let's go y equals, and let's do, what did I say it was? 1 plus cosine theta. So I'm going to do 1 plus cosine of theta. And I'm going to graph. So it has this little heart-looking shape, and I believe that's where they came up with the name cardioid. Oops. Again, I can't draw, but that's about as good as it's going to get for me. It's supposed to be symmetric, okay, across the x-axis. I just can't draw, okay? So that is a polar graph of a cardioid where A and B are the same, and it is symmetric across the x-axis, okay? Symmetric across the x-axis. In Calculus 2, polar graphs will come up again, and symmetry will help us with integration. So this is, right now, is just kind of an intro into the shapes that we might deal with in Calculus 2. So the next one is a cardioid with an inner loop. So this is when A is less than B. So here's my A and here's my B. So my A is 1 and my B, oops, my A equals 1 and my B equals 2. So A is less than B. So that means we're going to get a cardioid with an inner loop. In Calculus 2, this is one of the hardest shapes to integrate. So let's take a look at what this guy does. 1 minus 2 sine theta. 1 minus 2 cosine theta. So there you see we have this inner loop. So it goes like, oops. So it kind of looks like a cardioid, but then it keeps going in there. Oops, that's no good. Like that. So that is a cardioid with an inner loop. I've just heard them called, your book calls them cardioids with inner loops. I've just heard them called loops. So it just depends on the book, I guess. So in calculus, you'll be asked to find like the area of just the loop or something like that. And then we'll have to integrate from theta 1 to theta 2 of some 1/2 f of theta squared d theta. So this is what we'll have to do in calculus 2. But for now, this course is just about, so this is Calc 2. for now in pre-calc, we're just going to kind of get familiar with using these on our calculator. The next one is a limacon when A is greater than B. So in this problem, we have A is equal to 2 and B is equal to 1. So A is greater than B. So let's see what shape that gives us. 2 plus cosine theta. So let's go y equals 2 plus cosine of theta. And it's like a circle with like this flat head, okay? So we're gonna go over here to -1, and we're gonna draw like this circle with like a flat head to it, okay? So that's what a limacon looks like, all right? And again, we're gonna do more with this in a different class, but for now, we're just trying to get comfortable graphing these and identifying these on our calculator. So this is in general how we work. And if in general, if you want to find out like key points, you kind of pick the standard ones, 0, pi halves, pi, 3 pi halves, so on and so on, things that you know how to graph very well. And that'll help you get key points on a limacon, okay? So now kind of the coolest one is the rose petal. Well, I guess the limacon is pretty good too. So let's look at the roses. So roses have the form r equals a cosine of n times theta. So they have something inside with the theta, or r equals a sine of 2 theta. It does something totally different to the graph. So if you have r equals a cosine of n theta, and n is an even number, then you're going to have 2 n petals. If n is an odd number, then they'll just be n petals. So in this case, n is even, right? So n is even, so we're going to have 2 n petals, okay? So in this case, 2 times 2 is 4. So this rose will have 4 petals, but we're just going to graph it just in case. So we're going to go y equals, what did I say? 3 cosine 2 theta. So 3 cosine 2 theta graph. And we get the rose petal from the beginning, very similar to the one we did before. And as you can see, the number in front tells you how far out the loop will go. So in our case, we have 3. So it's going to go out to 3 cosine 2 theta. It's going to go out 3, out a distance of 3 before it loops back around. Okay, now let's look at this other one. This says 2 sine 4 theta. So this means that it's going to have 8 petals. So let's so 2 sine 4 theta. 2 sine 4 theta. And let's take a look at this one. Okay, so I'm not going to be too good at drawing this, so I'm just going to give it my best shot. Sorry guys, that's about as good as I can do. I'm not a legend in the art community. So that's going to be our rose petal. Let me see if that's kind of close. Yeah, that's good enough, right? Now, if you guys want to really go crazy, you can just try to do like y equals, and let's say 2, and let's make it go crazy. Let's say 16 theta. Or did I do 16 or 160? I did, oh no, 16. So that's what happens. Let's see if we do like 2.3 theta. Let's see if that does anything crazy. Oops, y equals. Yeah, so when you start putting decimals and fractions in there, it starts changing the rose petal and changing it to something else. So every time you do a little bit different thing with polar graphs, it changes what you would get. So kind of the goal is for you guys to just kind of be exposed to this is how polar graphs are kind of unique. They're really kind of cool. And remember, I'm only picking certain values when I graphed it. So way up here, I was only picking certain values, but if I wanted the full graph, I would have definitely needed to keep going, right? And, more than just 2 pi thirds, So a lot of graphs, you have to understand that you only get pieces of the graph for certain parts of pi, and it's hard to connect the dots unless you kind of know what you're getting yourself into, okay? So now let's look at the last one, Alemessant. I don't know exactly how to pronounce it, but that's the way I've heard it said. So hopefully that's right. And these take on the form r squared equals a times cosine of 2 theta, or r squared equals a sine of 2 theta. Now these are figure eights, basically. They look like the infinity symbol. You normally want your minimum for this, your maximum for this, and your step size for that. Okay, so let's try to graph this on our calculator, but our calculator doesn't have r squared. So what you do is you say r equals plus the square root of cosine 2 theta, and r equals minus the square root of cosine 2 theta. Okay, and now we're gonna, so cosine of 2 theta inside of a square root. So we're gonna say second function square root cosine of 2 theta. Okay, let's see what that looks like. So that'll be that. And then we're gonna do y equals, now we're gonna do negative second function square root of cosine 2 theta. Oops. And that'll be that. And now let's graph. And there you go. We have the two graphs and they make our figure 8 for us. So what we're going to end up with, oops. Is we're going to end up with this figure 8. R squared equals cosine 2 theta. Oh boy, that's pretty bad. There we go, that's better. That's about as good as it's gonna get for me, guys. I'm not, like I said, I'm not too good at this whole drawing thing. And then there's other types, you know, r squared equals sine 2 theta. That one's a diagonal figure 8. So you guys can practice that one. Instead of using cosine, you could use sine. But this is basically all I want to really talk about in this section. I think there was one question that they may ask you to do at the very end. So I just want to briefly talk about this, but I don't think I'm going to put this on the exam. This is just something that I want to talk about. So it says they may ask you to find the polar equation for the curve represented by y equals 1 plus 3x. Okay, so we have to find the polar curve that's represented by y equals 1 plus 3x. Okay, so we know a couple things about y. We know that x is, or I'm sorry, we know that y, you know, from our formulas, we know that x is equal to r cosine theta, and we know y is equal to r sine theta. These are two facts we know. So this could be r sine theta equals 1 plus 3 times r cosine theta, right? Now the thing is we have r's on both sides, and the problem in general with this is you want to get r by itself, you have to have them on the same side. So I'm going to subtract over, and I have r sine theta minus r cosine theta equals, 3 cosine theta equals 1. I'm going to factor the r out, and this is going to become sine theta minus r cosine, not r, 3 cosine theta equals 1, and then we divide. So then our answer would be r equals 1 over sine theta minus 3 cosine theta. And that would be how we could find the polar equation for the y equals 1 plus 3x. Okay? So this is just one technique that we can use. I saw one of these in the homework, and I just wanted to make sure that I went over it. I don't remember if I did it in the last video. So if you ever want to find the polar equation based on a rectangular curve, you can do, you know, this technique where you substitute in your x and your y and solve. Okay. All right, you guys, that's going to do it for 9.2. Really just a calculator section, learning how to enter these in on your calculator. I'm not going to go too much more in depth in this class on that. And that'll do it for this video. Thanks for watching.